Hello, let me welcome you to the Truckee Meadows Water Reclamation Facility. I'm Plant Manager Michael Drinkwater, and I have the pleasure to talk to you about our wastewater treatment plant that serves the cities of Reno and Sparks and the surrounding Washoe County. This facility receives approximately 30 million gallons of water per day. Wastewater is all of the water that gets used in homes and businesses in our community. Everything that goes down the drain makes its way here. Our mission is to take that water that has been contaminated by human waste, household chemicals, and business and industrial usages and remove the pollutants so that it can be safely returned to the Truckee River or reused for purposes such as watering the grass for our public parks. This facility was built in 1964 and is co-owned by the city of Reno and Sparks. We are what's known as a tertiary wastewater treatment plant, meaning we have three major segments of our treatment process to provide for an incredibly high quality of effluent leaving the plant. I hope you enjoy the tour as our plant staff walk you through the inner workings of our operation.
Hello, I'm Dave Brandt, the Operations Manager here at TMWRF. I'm going to walk you through the first set of processes that make up primary treatment. Primary treatment is the removal of pollutants through physical means such as screens or gravity settling. The first stage in a wastewater treatment plant is the headworks. At our headworks, we have two main channels that carry wastewater flow into the plant. Within these channels, we have screens that are comprised of vertical bars spaced a ½ inch apart. These bars are meant to catch all the big debris that may come into the plant, from bricks, tree branches, wallets, dentures. We even had a Christmas tree come in once. These screens take out all the large garbage first so that it doesn't make its way into the more sensitive equipment and break it. Perhaps a majority of things that get removed are disposable wipes. Contrary to popular opinion, these are not made to be flushed and cause serious mechanical damage. Some words of wisdom from a 30-year operator: no wipes in the pipes. Following headworks, where we took out all the large debris, the water moves to the grit removal, where we take out all the small, heavy, inorganic material such as sand and gravel. When the water enters into one of these two octagon tanks, the speed slows down to about 1 foot per second. At higher speeds, all the small particles in the water stay stirred up. With the water moving much slower in these tanks, it allows those heavier things to fall to the bottom, where they are removed and scraped off the bottom and sent to the landfill. The flow out of these tanks splits into one of 7 primary sedimentation tanks like the one you see here. The water is introduced into the middle and slowly flows out to the edges at a speed even slower than in the grit tanks. With the water moving at such a slow rate, it allows heavy organic matter to settle to the bottom of the tank. These settleable solids, which are dense enough they can settle over the 2 to 4 hours they spend in the tank. These solids form a sludge which is pumped off the bottom of the tanks and removed, so the cleaner water can move on to the next part of the process. You'll notice there's a circular ring in the tank. That is to capture floatable contaminants such as fats, oils, and greases. The ring prevents them from escaping, and the skimmer arm scoops them off to be disposed of. This ends the primary treatment process.
Hi, I'm Casey Mensler, the process engineer here at TMWRF, and I'll be taking you through our secondary treatment processes. Secondary treatment is the biological removal of pollutants that would otherwise be too small to remove through settling. These contaminants are either suspended in the water or dissolved in it. The way that they are removed is by adding in microorganisms such as bacteria and protozoa that will eat the organics and uptake the dissolved nutrients as they grow and multiply. This process is known as activated sludge, with the living organisms being the reason behind the term activated. You can see behind me in this tank that the water is quite a bit darker than what came out of the primary sedimentation tanks, and that's due to the introduction of that activated sludge. Now, you may also be wondering what all the bubbles are in this basin. Well, what we do is we pump in air into these basins. That way the microorganisms can respirate, they can be happy, they can eat, and they can consume all of the pollutants and nutrients that are inside of here. That is why these basins are termed aeration basins. There are many different ways to operate an activated sludge process, depending on what types of water quality need to be produced and what types of downstream processes a treatment plant may have. Here at TMWRF, we run what's known as an EBPR process. That stands for Enhanced Biological Phosphorus Removal. Now, EBPR is just an activated sludge operating configuration that not only removes organic pollutants, but specifically targets phosphorus. Now, the way in which we selectively grow the microorganisms to remove that phosphorus lies in the very first section of this tank. You'll notice that there are no air bubbles in this section. Most of the organisms that make up the activated sludge, they need air to live. The longer they go without that oxygen, the greater chance they have of dying off. These phosphorus accumulating organisms, or PAOs, essentially have their own little battery packs that are made up of phosphorus reserves and provides them energy, which allows them to stay alive throughout this section of the tank that's devoid of oxygen. And that allows these PAOs to have a competitive advantage since they can make it through relatively unharmed. Those PAOs are very effective. The reactive phosphorus that enters the basins comes in around 4 milligrams per liter and can be reduced down to 0.04 milligrams per liter. That's a reduction of 2 complete orders of magnitude. So these microorganisms, they suck up all that phosphorus and eat all the suspended organic matter that couldn't settle out in the primary sedimentation tanks. Once consumed and assimilated into the cell mass of the bacteria and other larger organisms, those pollutants can then effectively be settled out in secondary clarification tanks now that they're part of larger, denser organisms. Now these tanks behind me, these are our secondary sedimentation tanks. This is where we settle out all of that activated sludge and remove it from the water. Now, even after the activated sludge treatment, some solids may still have a hard time settling if they have the same charge. Particles that have the same charge tend to repel each other, and so they'll naturally want to stay suspended within the wastewater. So one thing that we can do to correct that is we can add in chemicals called coagulants. Coagulants neutralize those charges and allow a process known as flocculation to occur. In flocculation, particles will amalgamate together and form large, dense flocks that are easily removed by falling to the bottom of the secondary sedimentation tanks. Now, the sludge that falls to the bottom of these secondary sedimentation tanks is still teeming with microorganisms that are thriving and ready to keep working. So this activated sludge is sent back to the beginning of the aeration basins where it can continue to carry out treatment. It's important to maintain population control though, because if there are too many or not enough organisms for the food, then efficiency is affected. So as the microorganisms grow and multiply, some of that sludge is wasted out of the system and disposed of to make sure the right food to microorganism ratio is maintained. This ends the secondary treatment process. Here we move on to the start of our tertiary treatment. Tertiary treatment at TMWRF is the additional steps taken for further nutrient removal. At this stage, we've removed large debris, grit, settleable and suspended organic material, and phosphorus. However, it is extremely important that we also remove the nutrient nitrogen. Nitrogen and phosphorus both contribute to the process of eutrophication. Eutrophication is when bodies of water receive excess nutrients that lead to large algae blooms, which can remove dissolved oxygen and threaten aquatic species. TMWRF can only discharge 500 pounds per day of nitrogen to the Truckee River, which requires us to reduce the total nitrogen from its initial concentrations of around 45 to 50 milligrams per liter to less than 2 milligrams per liter. That focused removal of nitrogen starts here at our nitrifying trickling filters where we treat ammonia, which is the most common nitrogen-containing molecule in our wastewater. The water flows from the secondary clarifiers into the building I'm standing on where it gets pumped up to one of these 6 trickling filters. These trickling filters are filled 20 feet high with plastic media that water passes over. Filled with nutrients, this water encourages the growth of a biological slime layer that carries out nitrification. Nitrification is where ammonia is converted through oxidation into nitrate. Now, you may be wondering what these organisms consume since the organic carbon was largely removed earlier in the activated sludge process. The organisms in this process are called autotrophs and rely on inorganic carbon for their processes. If the aeration basins didn't do their job and let some of that organic carbon through, it would actually hurt treatment performance because we could grow competing microorganisms. Once fully converted, the water moves on to the denitrification process. Here at the denitrification building, we finish the process of converting that nitrogen. Denitrification is the process where nitrate is biologically reduced to produce nitrogen gas. The way in which that happens is through these reactors. These reactors are 26 feet high and 16 feet full of sand. The water is pumped through the bottom, which fluidizes the sand. Now, that sand fully fluidized allows a place where the bacteria can grow along the whole particle. Those bacteria need oxygen for respiration, but we keep these reactors anoxic, meaning without freely dissolved oxygen. Those bacteria, however, can utilize the available chemically bound oxygen that's in the nitrate, which was produced in the previous step. These organisms utilize this form of oxygen to breathe in, and then they breathe out nitrogen gas, which bubbles out of the water and joins the 78% of nitrogen present in the atmosphere naturally. You can observe the biochemistry in action at the surface where the bubbles are clearly seen coming out. So now all of the nutrient removal is done, and I'm here in the basement of our next major treatment process, filtration. This process is really just to polish up that water quality through passing it through one of 12 filters. Each of these filters contain gravel, sand, and anthracite media. In the filtration process, water comes in through the top and flows downwards through that media. The water easily passes through the gaps in the sand, but particles get stuck onto the surface of the sand, allowing for a much clearer, less turbid water to come out of the bottom. Gradually, these filters will get more and more plugged up with particulate matter. When that happens, what we do is we actually flow backwards through the filters and blow air in them to just break all of that accumulated gunk off, and we wash it out of the filters to keep them clean. These filters backwash anywhere from 3 to 6 times per day.
At this point, we've reached the final step for the water. We've removed the nutrients, solids, and organic contaminants, but we haven't yet removed pathogens. Pathogens are viruses, bacteria such as E. coli, or other microorganisms that can cause disease such as cholera. The water must be disinfected to prevent health concerns for the region. Here at Tumworth, we use sodium hypochlorite, also known as bleach, to inactivate and kill pathogenic organisms. Our bleach is more than twice the concentration of household bleach, so it packs quite a punch. The bleach is added at the beginning of the tank and is rapidly mixed. Following that, the water moves slowly down the basin, back and forth, where it spends a little more than an hour allowing the bleach to work its magic. We can't just let the bleach go out to the river though, otherwise it would go on killing native species. So we had a chemical note of sodium bisulfate to dechlorinate the water and prevent the reactive chlorine from reaching the receiving waters. All in all, it takes just under 24 hours for the water to make it from start to finish. At the end of it all, more than 1,200 pounds of phosphorus, 6,500 pounds of ammonia, and 60,000 pounds of organic load are removed every single day. Now don't think we forgot to talk about the fate of the pollutants we removed. While that was the treatment the water got, the contaminants also undergo their own treatment process. The sludges that were removed in the primary and secondary clarifiers move on to these large tanks behind me, each with a volume of over 1 million gallons. The goal of these tanks, known as digesters, is to stabilize these solids and break them down further. A whole host of microorganisms live inside these anaerobic tanks, meaning without oxygen, and during the reaction time they take complex organic molecules and break them down into much simpler compounds and reduce pathogens. These simpler compounds become more stable and easier to remove the residual water from. Once the solids have been digested from 20 to 25 days, they move on to the dewatering process where the water is removed mechanically through the use of centrifuges, creating a dried product that is approximately 15 to 20% solids. These biosolids are then trucked to the landfill for disposal. Tumworth produces more than 125 tons of biosolids every day. The digestion process also produces significant amounts of carbon dioxide and methane gas from the decomposition of organic matter. This gas is captured at the top of the digesters, cleaned to remove gaseous pollutants such as hydrogen sulfide, and then burned in boilers around the plant to provide heat for processes and buildings. This gas is also routed to a 20-cylinder engine where we produce just under 1 megawatt of power, enough to power up to 900 homes. Through resource recovery of gas, we are able to offset about 1/3 of our power demand and produce savings for our ratepayers.
My name is Kim Labor. I am the Tumworth Maintenance Manager. We have over 7,000 major pieces of equipment here at the plant. This includes pumps, electric motors, valves, instrumentation, and compressors like the ones you see behind me. We use a computerized maintenance management system to track and maintain each of these assets. Tumworth employs 10 mechanics and 6 electricians who perform several thousand work orders each year to keep the equipment available and running smoothly. And how do we know things are running smoothly at Tumworth? This woman will give you the rundown.
Hi, my name is Amy Egan, and I'm the laboratory manager at Tumworth. We are a certified wastewater laboratory in the state of Nevada. We are responsible for running over 30 different tests on various processes around the plant along with our effluent, irrigation effluent, and biosolids. Some of the tests that we run in support of our permit are ammonia, nitrate, nitrite, TKN, phosphorus, DO, pH, BOD, alkalinity, fecal coliform, E. coli, various solids tests, and metals. We have 5 chemists and 1 quality assurance officer that are responsible for running and validating almost 55,000 data points and 35,000 quality control points each year in order to provide the operations and engineering staff with legally defensible data so that the plant may provide the highest quality effluent to the community.
I hope this has been educational and helped you learn some of the effort that goes into cleaning the wastewater before we return it to the Truckee River in order to protect the natural beauty of our home, the Truckee Meadows. But it's not just equipment and chemicals, it's a staff of 64 dedicated people working 24 hours a day, 7 days a week that keeps Tumwarf #1 in the #2 business.